Welcome to this presentation produced by the Association for Preservation Technology, APT, with support from the National Center for Preservation Technology and Training, NCPTT. Please note that this presentation is copyrighted and reproduction, distribution, display, and use of any material in this recording without written permission of the presenter is prohibited.
Hello and welcome to this presentation that's sponsored by the Association for Preservation Technology and National Center for Preservation Technology and Training for the session on materials preservation. My name is Karla Salahshour. I'm a petrographer for Wish Janie Elsner Associates in Cleveland, Ohio. I have investigated and examined historic and modern concrete and masonry structures in North America and all around the world. And my practice is really set in the belief that the basics of microscopy and chemistry really haven't changed over time, but the tools we use and the materials that we've been examining and testing have evolved significantly. And so while the basics of these test methods are the same for modern and historic materials, the assessment becomes much more challenging and critical with historic materials, as different construction techniques, methods, and materials that were used historically are no longer available today or even used today. So the information that we gather from the lab studies is critical to the decisions that are made regarding the approach and the treatment of historic or heritage materials. And so it's really important to understand this historic context and the significance of the material and the project when performing the testing, when we're evaluating the distress or deterioration, and designing the repairs. So today I'm going to be talking about lab and field studies of concrete and mortar, specifically field assessment techniques and laboratory testing involving petrographic and chemical studies. Here are the learning objectives for this presentation, and we will review these at the end of the presentation. So my talk is centered on what, why, when, how, who can do this testing, how to do this testing, what the testing involves, and then what we do with the test results. So I'm going to be talking specifically about concrete and mortar, although this can be expanded to other construction materials. I could talk for hours on each of concrete and mortar separately, and then at length for each of the test methods that we're going to be going into. But this presentation is intended to provide the background on how concrete and mortar has evolved over time, specifics related to the field assessment and field testing of these materials, some sampling considerations, and then again, what we do with the samples during the investigation, specifically with respect to petrographic and chemical tests. So to start, we'll focus on what materials we're discussing. So we're starting here with concrete and cementitious materials. So concrete traditionally has been a mixture of Portland cement, sand, stone, and water that when mixed together create this hardened material. Given that we're also discussing historic concrete, it's important to note that significant material changes have occurred throughout history. Some of the big advancements were grinding technologies, developments with kilns at the cement plants. A big one was air entrainment in the 30s, and many other advancements to admixtures in general. And so because of these developments, we've had changes in cement fineness and concrete mix proportions, water to cement ratio, placement methods, and many other things. So we're also seeing the use of many different types of these materials like admixtures and supplementary cementitious materials like fly ash, and even other types of cement like high alumina cement shown here. And so because of these changes over time to these raw materials, we're occasionally able to provide a range or an idea of the time frame of construction for the material that's being examined. But I caution that this is not always the case in a petrographic examination. So talking again about changes in material, the picture on the left is a chunk of the concrete structural slab at the Pennsylvania Monument at Gettysburg. It was constructed in 1914. What's really interesting is that the concrete was so lean in this era that it was essentially pervious concrete, which we are actually designing for today, and you can see on the right. And that this mixture was actually quite freeze-thaw durable because it contained all of this void space to accommodate the expansion from liquid water to frozen ice. And historically, Portland cement cost a lot more than the labor. So the concrete mixes historically have decreased the amount of Portland cement, and we increased water content. And that increase in water content allowed us to place the material. And so our concretes had a lot of bleeding, for example. And this is one reason why dry shakes worked so well in the past in industrial settings. But in modern times, we've found that labor is much more expensive. So mixes would increase the cement content because the cement was actually cheaper than the labor. And so we led to decreases in water to cement ratio, meaning we had less water convenience, and therefore workability is now achieved by using admixtures. So we're seeing kind of a trend in the different mix designs because of the technology and developments in materials. This set of photos shows the first concrete street in the US. It's in Bellefontaine, Ohio. It was constructed in 1891. Shown here on the left under construction. On the right is a core sample that was extracted, sectioned longitudinally and polished. And you can see that there are actually two distinct layers comprising the pavement thickness. So the bottom portion is what serves as the load-bearing portion of the system, and the upper layer was installed to protect that body of the pavement from freeze-thaw distress. And freeze-thaw distress was a problem that had been recognized early on, but no one knew how to entrain air, or at least intentionally entrain air at the time. So what they did was provide essentially a face mix and a backup mix for a layered system. And again, remember, historically, cement was more expensive than labor. And so they needed a thinner cement-rich topping because that was going to be more expensive. So they provided a thinner topping layer to resist the elements. And then the thickest part of the structure, a slab in this example, was a cheaper, less cement-rich mix. The other thing to note is that historically, cements tended to be much coarser ground due to the high cost associated with grinding cement clinker. But then we saw developments in the mills and mill technology and grinding and the use of higher grade iron ores. And so it allowed us for the finer grinding of cements today than has traditionally been done. And so that brought a lot of changes to the properties of the concrete. And that again is an observation that can be made petrographically. So if we talk about mortar here, mortar is also a hardened material similar to concrete, but without the larger coarse aggregate. The paste typically includes a blend of Portland cement and hydrated lime, although we have seen mortars that contain solely natural cements that were lime sand systems that had slag cement even, and just many other blends have been used for mortar. As far as the material changes that we're seeing in mortars, there's a trend away from traditional field batching and mixing using solely Portland cement, lime, and sand and water. And we're starting to see an increased use of pre-bagged mixes. And while some of these pre-bagged mixes contain more traditional ingredients, some of them can contain additives. These additives can be admixtures, they can be polymers, they can be limestone fines, or any other SCMs. And so I want to note that there are many other construction materials that can be examined and tested in the laboratory beyond just mortar and concrete. Such materials may be dimension stone, brick, coatings, aggregate. For example, terrazzo even. We've looked at the terrazzo at Monument Plaza at the Hoover Dam that was constructed in 1937 on the left, or even recently constructed cast stone panels shown on the right in an educational building in Mexico City. So now that we've discussed the materials we're looking at, let's get into why we want to recommend lab testing and when do we recommend performing that testing. Lab testing can be extremely useful pre and post-construction. It can also be used during the construction process itself. Some examples of why we would do testing pre-construction are to evaluate the materials currently present on the structure, the condition or state of the material, assist with repair design, and depending on the extent of distress, realize it may be more advantageous to replace versus repair the material. So that's one thing that we can be involved in. Post-construction, lab testing can help to identify the materials that were actually installed, especially if that comes into question. We can help determine why unusual field test results were obtained, why a material may be aesthetically displeasing, or why something may be deteriorating. And so from a petrographer's perspective, it's important to talk to the person doing the studies, whether it's microscopy or other testing, to really try to develop the goals for the test and the questions that you want answered. So having a clear scope is important. And as is knowing the background of the project, primarily because the lab tests require some level of interpretation. So once we get a test result, what does that mean and how does that relate to your project? And so we recommend early and constant communication between the project team and the lab testing staff to give you the best results. Performing lab testing for modern materials is relatively straightforward, but when you add in a historic component, the evaluation becomes much more advanced. And so to perform an analysis on historic materials, you really need to have an understanding of the period of significance, understand the original construction techniques, and be able to identify significant elements and other aspects that are important for historic properties and materials. There's also a need for minimal intervention, and whether that's related to sampling or the types of materials present, but it may relate to the procedures used during repairs as well. And so the picture here is an example of trials of paint removal using strippers to try to not affect the natural board form finish texture for concrete repairs at the Anson Ford Theater in Los Angeles, originally constructed in 1931. Other considerations to know when performing an examination are related to material and environmental differences. Especially with stone masonry construction, stone material varies widely in the United States, depending on where you are. And so the types of aggregate can be related to this. Even raw materials such as fly ash can be very geographically very different. Some of the environmental differences talking about are variations in construction methods, especially talking about different repair methodology, even simply differences in just weather and exposure, and variations in codes. This picture on the right is from Perry's Victory and International Peace Memorial in Put-in-Bay, Ohio. It's a national park site. It was constructed in 1915 and is the world's most massive Doric column. This was constructed on an island, which made access to materials very challenging because they had to be ferried across the waterway. Doric columns were also a primary focal point of the main entrances of Grant Park Stadium, now called Soldier Field in Chicago, opened in 1924. And construction of this stadium was completed using steam shovels, which were the earliest type of power shovel or an excavator. And you can see horse-drawn carriages circled in the images here. How do we actually perform this testing? We like to say that the examination of materials and the problem at hand really starts in the field and that anyone can make initial observations. So again, we like to think that the investigation starts in the field much earlier than when samples arrive in a laboratory. And anyone can use methods that we use in the laboratory that can easily be adapted for field use. And so someone who is trained to look for certain features can be very valuable to the project team. And so we recommend, if the budget allows, to allow lab or testing staff to visit the project site and be present, especially during sampling, to make sure that the extracted samples are the best choice for the problem at hand. Shown here are illustrations of a macro tube. This was a piece of equipment that was developed in the WJE Cleveland laboratory to allow for microscopic imaging of field conditions. It's essentially just a box or a container that eliminates external ambient lighting, and you can use it to introduce overhead or low angle light. It can also be used with a camera for photo documentation. The picture on the right is a wooden version of the macro tube. The underside of that box is shown. That wooden box has an included magnifying lens and has an external flashlight to introduce that lighting. So this is a picture that we could take using the macro tube in the field of a bed joint. So you can see the brick masonry on top and bottom and the mortar joint in the middle of the image there. You can see the texture of the surface of the joint. So some of that paste has been eroded away, exposing some of the sand aggregates. But it's also neat that you can see a spider web that got deposited on the surface of that joint over time. So talking about field techniques and field tools, we recommend having in your tool bag a hand loop, a field microscope, a flashlight, a camera, and perhaps a camera fitted to some type of microscope like the macro tube. We also have found that digital microscopes, such as the one shown on the right, are getting much more sophisticated and inexpensive and can be quite useful in the field just to take a higher magnification image. And you don't have to use advanced, expensive equipment to take a look. But we do feel like the use of photo documentation can be important during field studies and can be useful, especially when a petrographer is involved in a project. So this is an example of the use of a digital microscope that was hooked up to a laptop in the field to take photos. Again, this was an inexpensive way to get up close field images that were then used to discuss testing options with the lab. These pictures are from the Edison Memorial Tower. It is a 131-foot concrete tower with a 15-foot bulb on top. It was designed by John J. Early and constructed in New Jersey in 1938. Early sought to improve the appearance of concrete and wanted it to look more like stone, so he exposed the aggregate. And his work first began in the 1900s. And by 1910, he developed this technique of mixing aggregates into the concrete, scrubbing off some of the paste before the concrete had fully cured, which resulted in exposure of the aggregates on the exterior surface. He referred to this as architectural concrete, and it became known as the MOSI method and was actually developed into an institute, which was an organization of precast concrete manufacturers who practiced this method. So the feature shown in the left image shows that exposed aggregate surface, and that could again be seen in the field with the use of a field microscope and a camera. The middle image shows another example of a two-layer system. So with a face mix above the line and the backup mix below the line. And note that this feature would not have been able to be seen in the field. So we required a core sample be extracted and prepared in the laboratory in order to observe anything with depth from the surface. But seeing the image on the left, that type of surface features could be collected in the field and did not require the use of expensive microscopes in the laboratory. One of the other techniques that we use are different lighting techniques, specifically different angles of lighting. And so this is the same image shown with overhead light on the left and low angle light on the right. And on the right, you can really see that we highlight the grooves on the surface of this core when we change the angle of our lighting. Another technique we use in the field is simply the use of water. So spraying water on the concrete surface can really give us information about possible post-construction practices. So here on the left, water was sprayed on the surface, and on the right, I've circled beads. So the water was not absorbed, it actually beaded on the surface. This was something that we would expect to see from something that was treated with a sealer, for example. And so if this observation was important to our investigation, we could then further recommend perhaps chemical testing to chemically detect the presence of a surface material like a sealer and to determine its composition if present. So once some of those observations are collected in the field, we need to start talking about sampling. The first question that we really should discuss with the project team is, are samples actually required to help answer the questions at hand? This is the ASM building. It's the world's largest open air geodesic dome in Geauga County, Ohio. It was designed by Buckminster Fuller and constructed in 1959, and it is listed on the National Register. So we went out onto this site and we noticed that there were streaks of white secondary deposits or efflorescence shown in the upper right image with those arrows. And these streaks were coming out of the partial height of the wall. And usually when we see that, it indicates moisture migration through the structure. And so in the field, we recommended performing inspection openings to determine the source of those leaks. And so for this project, trying to determine how and why the structure was leaking could perhaps be solved just with field studies, and sampling wouldn't necessarily be included. However, if we started talking about repairs to the concrete structure, and if those were warranted, maybe that's when we start thinking about if concrete samples should be taken specifically to assess the condition of that concrete. And so we did, in fact, take samples out of this wall, and we found through those studies that we had well air and trained concrete. It was testing over 4,000 PSI, but we started seeing freeze-thaw distress, which is highlighted in the image on the lower left of the page. And so those vertical cracks shown in that image are characteristic of freeze-thaw distress. And this was interesting because even though we had well air and trained high strength concrete, we still had evidence of freeze-thaw distress. And so even good quality concrete is susceptible to deterioration over time. This is another example of how sampling and core examination provided more information than could just be seen in the field. And this example was from Fort Mott in New Jersey. It was constructed in 1896. Originally, the studies were simply focused on the efflorescence seen on the walls of the fort, which you can see on the left image here. The walls were constructed of mass concrete, and at the time of construction, there was no way to mix and place these large batches of concrete. And so we had a lot of cold joints in the walls. And in the field, we saw that the efflorescent staining was a result of moisture migrating through these mass concrete walls at all of the cold joints. So when we took core samples, because we knew we were going to do some concrete repair work, we wanted to understand the material that was used in construction. We identified various concrete mixes within the cores. So again, similar to the construction we saw for that concrete pavement in Bellefontaine, Ohio. So again, we had a more durable and likely more expensive face mix above the yellow line in the right image. And we had a cheaper, less durable backup mix that comprised the majority of the thickness of the walls here. And today we don't typically use this two-layer construction specifically to achieve freeze-thaw durability. We have technology and admixtures now. So now we simply just add air and training admixture and lower our water to cement ratio to get that durability. Although I am biased, I work in the laboratory, I do think samples can be instructive, but only if they're carefully selected and extracted. We also need to give credence to the historic aspect of some of these projects and pay careful attention to where the samples are extracted to not alter a significant component or fabric of the structure. So that leads to more discussion on samples. So I mentioned that petrography and lab testing is somewhat interpretive, and interpretation of the test results can be extremely important to the project. And so in order to provide a good interpretation, we really like to have as much information as possible provided with the samples. And so these are examples of what information we would like collected and sent with the samples to the laboratory. And so things like the job location, the context in which the samples are collected, any background information, here where the samples are taken, a description of the samples, what testing is required. But we really like to have as much additional information as possible. A mixed design can be very, very instructive, and if not a mixed design, batch tickets, and exposure conditions of the samples themselves. So most labs will have some sort of sample submittal form that prompts you to provide and supply this information. So sampling is performed in the field, but we really recommend talking specifics of the sampling process with the testing staff. Many different types of samples are acceptable for a test, and some types of samples are going to be easier to obtain than others. So for example, whether we're talking about a drilled core or if we have a cylinder available, powdered samples or fragments of material. Our test results are really only as good as the materials supplied for the testing. And so the better quality the material, the better the results of the test. Also, if we're specifically investigating a problem, we recommended taking cores representative of each type of distress and also including a control and non-distressed core. Especially for masonry, we like to encourage the use of mini cores, so small diameter, say about 1 inch in diameter and size. They can be extracted using a masonry bit on a handheld drill, so you don't need some big bulky equipment. It's a great way to extract samples of mortar because it allows you to collect the masonry on either side of the joint, and having that interface can allow us to provide commentary regarding the bond and the initial bond. Other benefits of using mini cores is that you can minimize the sample size and you can attempt to obtain intact core samples. So rather than extracting a pulverized material from a mortar joint, which we really can't do very much with petrographically, with using a mini core, you can attempt to extract a core sample. So rather than having pulverized material, we really like to have an intact chunk or chunks of mortar. Don't worry though, in case you cannot get intact samples out, there are ways that we've developed in the laboratory to handle small fragments or rubble. We can epoxy impregnate these samples either under vacuum or not. Let that epoxy cure and we can still prepare cross-sectional surfaces. But again, we really recommend you getting in touch with the lab staff to find out what size samples, what orientation of extraction is best suited for the testing that you request. One thing to note is that the core orientation can have a significant effect on the test results. For example, core samples that are tested in compression really should be tested parallel to the direction the concrete was placed. So for a wall or a vertical element, though, that can be problematic. And we're typically extracting core samples horizontally. So shown here, we have a vertical element. We extracted a core sample horizontally. The problem with this is that excess or free water in the concrete rises and it can get trapped beneath aggregate particles. And this creates water gain voids along the paste to aggregate interface. And those water gain voids are shown with arrows in the left photo. The sketch on the right illustrates the orientation of these water gain voids beneath the coarse aggregate in the in situ orientation. So we took the core out horizontally. That is how those features would be oriented. So when we take that core, that horizontal core, and then rotate it 90 degrees for compressive strength testing, as shown on the right, those water gain voids start aligning with the direction of loading. And so this can really reduce the measured compressive strength because of these voids. And so you may get a low tested compressive strength, but it really may not be indicative of how the material is performing or strength-wise is acting in the field. And so again, understanding the core orientation can be very important when interpreting test results. Samples also need to be properly cared for after extraction and during shipment. So making sure they're properly wrapped and not allowed to break in the field. This picture on the right is an example of a core that was bagged upon extraction. And so it trapped in some of that coring moisture. When it arrived in the laboratory, all of that dark material on the core perimeter was actually alkali silica gel that exuded out of the paste. So think of the concrete core as this living object that can change based on the ambient conditions that it's subjected to. Once we take samples, we then need to figure out where the testing starts. So does it start with physical or mechanical testing, chemistry, or petrography? Some of the common laboratory tests included in projects can be petrographic analysis, an air void study, cement content, chlorides are very common. We can get into more specialized testing like freeze-thaw resistance and alkali aggregate reactivity. However, often studies do begin with petrography. So just taking a quick look at the material petrographically and then determining from there what other studies may be necessary. So for this presentation, I'm going to focus on petrographic examination and chemical studies as it relates to ASTM-C 1324 of mortars. But just know that there are a ton of tests that can be performed in the lab depending on what information you need for your project. So starting with petrography, what is petrography? It is a branch of geology that has been applied to construction materials, and it simply involves the microscopic examination of samples. Petrographers are commonly asked to characterize materials, identify distress mechanisms, predict future performance, and to evaluate repairs. And this work is done by preparing samples, examining them at higher magnifications, really through the use of two main microscopes. So we have the polarized light or petrographic microscope shown on the left and a stereo microscope shown on the right. So we use these microscopes to observe optical features of the samples. And then based on those observations, we interpret them in the context of the project. So this is an image that one may see in a petrographic report. This was taken with the stereo microscope. So it is the lower magnification of the two microscopes. In this image, you can see the coarse aggregate. You can also see a significant number of air voids and fine aggregate. So bulk gross features are collected with the use of a stereo microscope. When we start talking about higher magnification, we use a petrographic microscope. In that microscope, we use a thin section. And if you are not aware of what a thin section is, it is a slice of concrete that is typically ground down to 20 to 25 microns. For reference, a human hair is 100 microns thick. And so it's about a quarter of the thickness of a strand of hair. And the reason why we grind it that thin is that it allows light to be transmitted through that slice of concrete or mortar. And then again, we observe optical properties of the material, and it allows us to identify components of the mortar of the concrete. And so on the left are large and small format thin sections. On the right is an image that we can take under cross-polarized light. This is an example of what could be delayed ettringite formation. So we have a gap around coarse aggregates that's been infilled with ettringite. And so having a trained eye of what to look for optically and being able to characterize the aggregates, the paste, and secondary deposits then allows us to interpret the distress mechanism, in this case, delayed ettringite formation. This is an image that you may see in a petrographic report from the petrographic microscope of a thin section. This lighting is in plain polarized light. And if you remember the previous photo from the stereo microscope, we were able to see full coarse aggregate particles, but we're at such a high magnification here that we are only seeing a small fraction of the coarse aggregate. but we're able to start identifying cementitious materials. So you can see the Portland cement that's been identified. The fine aggregate is larger, air voids, and we typically use a blue dyed epoxy for thin section preparation. And so that blue dyed epoxy infills voids in our thin section. So the crack in those air voids there are highlighted by that blue color. So this is an example of something that we could differentiate in thin section using a petrographic microscope. This is the difference between a historic and a modern cement. So I mentioned before that we've seen significant changes in the material over time. And one of those changes was to the grinding operations at a cement plant, which allowed for the Portland cement to be ground finer than was previously done. So on the left is historic coarsely ground baylite nest, and on the right is much finer ground Portland cement. And if you think about it, the finer material is going to be much more reactive and increase that rate of strength gain. And so think of how big of an impact achieving a higher strength at an earlier age can be to the construction industry. It can make huge advancements in construction. And so something that may seem so minor, like finer grinding of cement, can really have a snowball effect on the change of materials, the design of mixes, and the placement methods for forever. This is another example of how we identify features in thin section. So we can identify the aggregate composition. We can identify the cementitious materials. So identified with yellow arrows here are Portland cement particles. Again, this was historic concrete from 1928. So we tend to think of those as being very coarsely ground or about the size or greater than 100 microns. We also detected hydrated lime in this sample, and there's a lime lump shown in the upper right portion. And again, we can identify void space as infilled with that blue dyed epoxy. Another example of how we can characterize materials. This is a masonry cement mortar. So a masonry cement mortar is going to have very characteristic ingredients. So we look for things like Portland cement, shown on the left, fragmental limestone, as shown in the middle, and air entrainment. So having a lot of small spherical voids, as shown in the right. And this mortar was extracted from a building in Kansas, constructed in 2005, so a modern mortar. So once we make our observations petrographically, we typically perform chemical studies in conjunction. For concrete, those chemical studies may include chlorides, pH, or an alkali profile. And for mortar, we typically perform C1324 chemical studies. We can do X-ray diffraction, total sulfur, or cement content even. So I want to specifically discuss APT-NCPTT 1324, which is the standard test method for examination and analysis of hardened masonry mortar. This standard includes both microscopic examination of a thin section and chemical analyses. So we're currently seeing a trend moving away from these C1324 studies, and I found that a lot of clients want to perform C1324 solely to receive the mortar proportions to be compared to APT-NCPTT 270, and that is then what is recommended for repointing. And I found that little consideration is given to the masonry, the properties of the mortar, the exposure conditions, the current condition of the building and the joints, and many other considerations. And so I prefer to think of mortar repointing analysis and designing a mortar rather than selecting a mortar. I'm also finding that the information obtained from a petrographic examination is often sufficient for the project team, and that further chemical studies in C1324 really aren't needed by the project team. Regardless of that, though, I do want to go through the C1324 studies so you have some background on what can be done on mortars chemically. So like I mentioned, C1324 starts with thin section petrography. And so we prepare a thin section and we examine it with a petrographic microscope. We identify the composition of the binder. For example, on the left, we have slag cement and Portland cement. We look at the aggregate composition, the size and distribution of the aggregate, any voids. We also look for leaching that may have occurred from the paste, say during exposure of moisture and moisture migration through joints over time. And we also look for a general competency of the fragment. So is it hard? Is it soft? Does it fall apart and crumble? And once we make those petrographic examinations, we start our chemical testing. The chemical testing includes a lot of different types of physical test methods. And so the analysis that is collected from all of those different test methods are shown here in these two tables. Those results from those tests are then interpreted and input into calculations, and those calculations are based on certain assumptions on the mortar and based on the thin section petrography. And those then provide the information in this table. So most people will immediately jump to this red box region to see what the volumetric ratio and the corresponding ASTM C270 proportions are. But I want to note specifically for this example, the mortar was leached and that was examined petrographically. And so that means that the hydrated lime percentage that was calculated chemically may be undersanded or underestimated, and therefore the mortar may appear oversanded. And so this is just a reminder to you that if you use C1324, that these are still estimates and that many assumptions go into these analyses. And because C1324 requires all of these assumptions, there really needs to be good communication between the petrographer and the chemist to obtain the most accurate results. So I mentioned the results are compared to ASTM C270. This is the standard specification for mortar for unit masonry. The standards includes a table for performance specs, but those properties can't be obtained from microscopy and chemical analysis. So what we do is we compare our findings from the studies to the proportion specifications, and we match it as best as we can to, say, a type M, S, N, or O. What we're also able to do is a point count analysis on a thin section, and that allows us to collect a binder to sand ratio. So what we do is we count total points intersected as paste, void, or aggregate. We convert those to volumetric percentages, and then we can use an empirical equation developed within WJE to provide that binder to sand ratio. This point count analysis has been used to supplement the chemical analysis testing and helps to provide more accurate information to the chemists for their calculations and for their assumptions. So again, I just want to caution the use of C1324 as such a quantitative result. Understand that those results are obtained through calculations made with assumptions based on the materials. And so there's always room for interpretation, which can affect those results. And again, communication is essential between the lab staff and the project staff. And keep these results as a guide for repairs. And note that it may not even be possible to recreate a historic mortar with modern materials. And so even if you could use historic materials, you really can't recreate the history and the exposure over such a long period of time of that material or mortar being studied. So after we collect all of these observations from our testing, what is done with that information? So it can be used for the conservation of materials. So it requires an understanding of the history and significance of the concrete heritage. Again, we assess the characteristics and the condition of the material. We can also use documentation, but we can take those findings and develop a repair approach that follows preservation guidelines to account for minimal intervention to match the characteristics and appearance of repair work and provide a level of durability you need moving forward. And this was the scope that was taken for the Salk Institute project that we spearheaded, originally constructed in 1963. Some of our findings can be used to develop repair mix designs. So we prefer to understand the material of what we're attempting to fix or repair, hence why we collect the samples, we perform laboratory testing to really know what material was there originally. And then in order to do that, we collect all of our observations and we can back out an original mix design. I want to note though that doesn't mean that even if our volumes of our constituents are the same between the original material and the repair material, it doesn't mean that the concrete or the mortar will act the same. And that's because we often don't have the same materials available for construction. So for example, stone or aggregates, sometimes those original quarries are no longer producing. And so we need to use a different material. For Portland cement, the cement we use now is much finer and of different chemistry than historic cements. Also, would we even want to use historic cement using ancient mixing and placing techniques? Likely no. Our technology today allows us to optimize our mix design and provide greater durability. So what we aim for is to match the materials as best as we can. Note that it's hard to match a poor quality concrete. So in moderate climates, poor quality concrete can actually last a long time, but in freeze-thaw climate, like where I'm in Ohio, poor quality concrete really doesn't last very long at all. Good quality concrete is obviously much easier to match. And so regardless, our repair materials are always going to be slightly different when we design a repair mix for a historic structure. So in summary, from this presentation, I hope you understand the importance of historical context when evaluating historic materials, that you now understand how materials and construction techniques have evolved over time, that you can tailor lab studies to your specific project, and that some of these lab techniques that we use in the lab can also be simplified and adapted to be used in the field. We like to say that lab testing helps tell the story of the structure. So not only can we provide an analysis of the current condition, we can also use that information to help for the restoration project and for the repairs. And again, I'm going to reiterate here that the basic principles of the lab testing apply, whether we're discussing historic or modern materials. But the approach we take and the choices that are made are much more important for historic structures because of the cultural and heritage components. And so the lab studies become very important as they dictate so many downstream decisions. If you would like more information, some references to ASTM or a great concrete petrography book are provided here. But that concludes our presentation. I want to thank you for attending and thank you to the sponsors. My contact information is provided on this slide. Feel free to reach out to me or to APT with any questions. Thank you.